Good morning. Welcome back to the second day of the Convergence symposium of the Austrian Academy of Sciences. We have two very exciting sessions of the symposium ahead of us today, as well as the two more discussion groups, as well as short talks around lunch, and then a wrap-up session at the end of the day. It's my great pleasure for the first session on interactions to welcome Natalie Sebanz from the Central European University on stage. Please.
Good morning, everyone. Can you hear me well? Great. So yesterday, we talked quite a bit about extensions and augmentation. And you could say that really what we're talking about here is ways of using technology to expand our action possibilities. Now, often we don't just want to act on objects in our environment, but we actually want to interact with each other. So there's a nice picture that's not coming up. I have no idea why. I think the whole thing got stuck. Here we go. All right. Seems to be a particular picture that takes time to load. So we often engage in social interactions with each other where we coordinate our actions in space and time in order to achieve common goals. This is also known as joint action. And this ability to engage in joint action allows us to expand our action possibilities, perhaps in other ways than using technology does. So once you start thinking more about joint action and you look around, you realize that it's really everywhere. It's a very common phenomenon that human societies rest on. So the times where we used to go hunt together are past us, but there are many other things people do together. They're fixing things, they're performing surgery, they're passing the salt. They're also often engaging in joint activities for the sheer pleasure of it. So if you think about doing music together, dancing, or team sports. And interestingly, these are not just enjoyable for the people who engage in these activities, but also for the audiences. So often we also seek out performances because we want to get particular aesthetic experiences that come from watching joint action. And finally, there are contexts where we engage in joint activities, not so much because we want to do something together per se, but we want to learn from each other. So there are contexts of cultural transmission where people coordinate their actions because by acting together in this way, the more expert person can pass on knowledge and skills to a learner. So in my research, the key question that I have focused on is what are the neural and cognitive processes that allow us, that make it possible for us to engage in joint actions. And from there, we can also ask, what does it feel like to act together? When and why is it enjoyable? And what can we learn from all this about social interactions involving interfaces of the digital and the living, in particular human-robot interaction? So I've organized this talk around a few key principles. The first one that we have seen across many, many studies is that people integrate the actions of a task partner into their own planning. So they do this spontaneously, even in situations where they could ignore the other person, where it's not strictly necessary to pay attention to what the other is doing, and they very much do this when coordination is indeed required. So let me give you a simple example. This comes from an old study that we performed a long time ago, and it served as the basis for many other studies. I'm first going to tell you about a task that can be performed by a person all by themselves, just using their left and their right hand. And then I'll tell you how we split up this task between two people and what happens when you do that. So the task requires you to respond to color. And let's say you need to respond to red with a left key press and to green with a right key press. You can imagine you have two keys in front of you. That's your task. In the actual experiment, the keys are not colored. This is just for you, so it's easier to imagine and remember. Okay, so red, left key press, green, right key press. Now, as you can see, the stimuli sometimes appear on one side and sometimes on the other side. And this actually makes a difference for people's performance. So even though the location is completely irrelevant, it influences people's response times. If you measure how long does it take people to respond, you see that they are always faster in the compatible case, where let's say you need to respond with a left key press and the stimulus happens to be on the left, compared to a situation where you need to make a left key press because the color is red, but the stimulus is on the right. Why is that? It is because you cannot ignore the spatial location. It's something you automatically process, and it activates a corresponding response. So if I see something happening on the right, my right hand wants to respond, and then I need to tell myself, no, actually I need to use the left hand, and this creates some kind of conflict that needs to be resolved, a conflict between two actions that needs to be resolved. All right. Now, why am I telling you about this? I'm telling you because there are really two tasks here, right? Responding to red, responding to green, so we can distribute this task between two people. Now, before I tell you about that, I'll tell you about the most simple version, where we had one person doing the task, responding just to one color. And as you can imagine, when you have people responding just to one color, so acting or not acting, depending on the color, you don't see this difference anymore, because it doesn't matter whether the stimuli are left or right. There can't be a conflict because you have only one action, right? There can't be conflict between left and right. But now the question is, what happens when we ask two people to do this task together, such that one person responds to red and the other person responds to green? If you're ignoring the other person, then everything should be just the same as when a single person is doing this using only one response, right? So there's no conflict there. However, if you are including the other person in your planning, the whole thing might be a little bit like the bimanual version, where you're using your two hands. So this could give us some evidence that people are indeed considering the other, taking them into account, including them in their planning. And this is also what we found. So you see that there is the same pattern here, the same compatibility effect, when people are doing this with their two hands and when they're doing this together. Now, what about if your partner is a robot? The group that studied this actually also included a belief manipulation. So there were two groups of participants here. One group was told, this is a very dumb machine-like robot. It's been programmed to respond in response to a certain color. The other group was told, this is a human-like smart robot that has its own intentions. And then the task was the same. So it was again this red-green task with one person responding to one color and the robot responding to the other color. What they found is that it makes a real difference what kind of belief people have. So if people believed that the robot was human-like, the effect was there, similar to the case where you have two people acting together. But if they believed that the robot was machine-like, the effect was completely gone. So this suggests that regardless of appearances, it is really attributions of intentionality that can be very important when we have these kinds of interactions. Now, let's move on to a situation where people actually need to coordinate, clinking glasses. How is that done? This was an EEG study, and we used a similar logic in the sense that there was a unimanual action, one person grabbing a glass and moving it as if to clink it. We had a joint action, two people grabbing a glass each and clinking it, and a bimanual action where one person would grasp both glasses and then move them and clink them together. Okay, now, what we actually wanted to know is what happens in the brain, what happens in terms of action preparation before people are starting to act. And with EEG, we can do that. So we had two people facing each other, there were the two glasses, and in between we showed them stimuli telling them what to prepare for. So either we told them, you don't need to do anything this time, just relax, or we told them, prepare for acting alone, using just one hand, prepare for acting alone using both hands, or prepare for acting together. And there were 1.5 seconds during which they prepared before we told them, now execute the action. So this gives us a window into this planning process, and we can see again, is planning a joint action similar to planning a bimanual action, or are people only planning their own part? There is one particular component that we can make use of here. It's called the CNV, contingent negative variation. And this component is relevant because we know from earlier studies that it is higher when people are planning to perform a bimanual action compared to a unimanual action. So we already know that when there is more complexity in the planning and you need to plan something relational, there is more negativity, and this is a marker of motor activation, so we can also simply say there's more motor activation ahead of time. And so now we can look at this particular component and ask, well, what is this like in the joint context? Is it like bimanual, or is it just like acting with one hand only, so you're ignoring the partner? And the answer we got from the results is here very straightforward. Bimanual is the dashed line, and you can see that it's right on top of the joint condition, and they're both higher, so there's more motor preparation there than in the unimanual case. So this tells us that there is a stage in action planning where people are really including the other in their action planning as if the other was their other hand. So acting together and acting with your own two hands can be very similar. We've also extended this in recent work, getting rid of the objects and having tasks that are a bit more sort of interactive, if you will. So this is a hand game where people are moving with to have their palm either facing outwards or inwards. And if you imagine two people doing that together, you end up with 4 different configurations. So people might be doing the same, both having their palms facing outwards or both having their palms facing inwards, or you could have opposite configurations. Again, we gave them cues ahead of time, and then later on specified the full action and told them now to move. And in this particular case, we either gave them the full information, so we told them this is the hand shape you need to produce, and your partner needs to do the same. Or we told them your partner needs to do something different, so the opposite. So they had the full information ahead of time. And we can compare this to a condition where we only give them information about their own part. Here they know how to move the hand, but they don't know what the partner is going to do. Does it make a difference or not? You know what you need to do, right? But in one case, I'm also telling you, you're going to do the same. In the other case, I'm not telling you anything about that. So that tells us, do people care about relations? And then we have an interesting condition where we only tell them about the relation. We tell them, you're going to do the same. But we don't tell them what kind of hand shape they will have to produce. We only tell them just before they start acting. So this tells us whether the pure relational information can still be used. And then there is a condition where they have no information ahead of time. It's the CNV, again, that we're looking at here because we like it. It's this nice marker of motor preparation. And we see a scaling here in accordance with the information that was provided. So there is the most activation, the most preparation when people have full information. So they know what they need to do and they know about the relation. A little bit less when they know what they need to do, but they don't have information about the relation. And then you see there is also a difference between having no information and having only relational information. So telling people you're going to do the same or you're going to do the opposite from each other helps them prepare, even at the time where they don't know what exactly it is that they are going to do. And all of this happens in our motor system because we also did some frequency analysis with EEG where we could, again, use a typical marker. It's called mu suppression. It's a marker of motor activation. And we found that this is there not only when people have information about their individual action, but also when they have this relational information. And we've only done this so far with pairs of humans, but I think this approach could quite easily be extended. So for instance, yesterday we heard a lot about people wearing prostheses, so you could actually imagine having a partner with a prosthesis, perhaps moving in quite different ways, and then we could sort of investigate to what extent people are able to include actions that are different from the ones they normally perform. Or you could have a robot partner, or you could add some extra thumbs, not just one, but 2 perhaps. All right. Now, how do people coordinate their actions? I'll make this very brief. There's a lot one could say here. Just want to run it at a time. Sorry. Yeah, I'll make this fairly brief. The important principle here is that people are always trying to predict each other's actions, and therefore it makes a lot of sense to act in ways that are predictable. So when people are acting together, they're trying to make their actions predictable for each other. Now, how do they do that? There are 2 ways. One is you can try to reduce variability. If you're acting in a very steady way, it makes it easier for other people to predict what you're going to do next. So for instance, I was once in India and, you know, amazed by all the traffic there, and when you have these roundabouts, it's crazy how much is going on. But then you have some people who just follow a straight trajectory. They're not looking left or right, and everyone else kind of understands where they are going, and you have this marvelous coordination because this person is just being so straight and so steady. So that can be one way to coordinate. The other is you're exaggerating things. You become very communicative. So for instance, if you see me grasping a bottle like this, very easy for you to guess, at least people sitting on this side, that I'm going to grasp the left bottle, right? So I've exaggerated things. I've made it easy for you. That's another way you can increase predictability. Here's one study where we looked at this, again, in human-human interaction. It's a very simple task where people have a mouse cursor, and they move the mouse cursor from a spaceship to a planet. And their task is to arrive at the planet at the same time. The only help they have is a little auditory beep. So the beep tells them, now you can initiate the joint action. And what we manipulated was whether or not people could see each other. So when people cannot see each other, how do you act in synchrony? How do you arrive in synchrony? The only thing you can do, really, is try to be predictable by reducing variability. However, if you can see each other, then you might, you know, use a different strategy, and you might want to exaggerate your movements, because perhaps then this is the better way to coordinate. And that's exactly what we found. So when there is no vision, we found that they are acting faster, and the variability is indeed reduced. So that is the strategy they use in order to coordinate when they can't see each other. And you can also see this when you look at partial correlation. So what predicts the asynchrony between people? The best predictor is the variability here. So the less variable, the more synchronous they are. Now, again, taking the same task, but in a version where they can see each other, we see something very different. We see that when we look at the area under the curve, so how much curvature is there in the movement, it is higher when they can see each other than when they cannot see each other. And so when you look at the same kinds of correlations, what now predicts the asynchrony is the curvature and also the variability of the curvature, because you don't want it to be too sort of variable, okay? Now, we can also look at human-robot interactions and look at these principles. Here's work by Anka Dragan, where she had robots grasp a bottle, and people were asked to predict which bottle the robot is about to grasp. There are also versions of the task where there is actual interaction. And just as I showed you before, there were these two principles, either just sort of acting in a normal way or acting in an exaggerated way. So the robot would also make this kind of trajectory to make it very salient where they are going. And they wanted to know, how do people predict actions? So does it actually help them to have a robot exaggerate their movements in order to predict what the robot is about to do? And the answer is yes, it helps. Just as in the human case, this is something they can make use of. When the robot is overdoing it, so they also had a condition where the robot would do something that humans don't do, which was to invest a lot of effort from a human perspective and go all the way around. And that's something people found simply strange. So it didn't help with the prediction, and they didn't like it either. So it was too different from what they expected. And they also showed that when you have a collaborative task, indeed the collaboration is more fluent when the robot acts in this communicative way. So I think this, together with the other study on human-robot interaction, also tells us that we need to think not just about appearances, but we really need to think about the behavior and what kind of expectations people have. And often, even if you have a robot that doesn't look human-like at all, if you have features of human behavior, it will get people to feel that there is a joint action going on. Now, coming towards the end, towards the last part, I want to talk a little bit about the experience of agency. So agency is our feeling of controlling events and controlling our own actions. And in the context of joint action, it's quite interesting to ask what kind of feelings of agency people have, because not only could joint action change your feeling of individual agency, but it could also lead to new experiences that you can only have in a context of joint action, such as feelings of joint agency or we agency. One very nice overview paper that recently came out by Janine Leur, made this distinction between different kinds of we or joint agency. So there is what she calls independent agency. These would be situations where, let's say, you're doing a puzzle together, but in such a way that you can work quite independently from each other, and you're only later putting the different parts together. So your experience might be, we're doing something together, but at the same time you feel quite separate. Now, with shared agency, the idea is that this could be something like moving a sofa together. You feel you're doing something together, but you can still, to some extent, individuate your contributions. I'm moving this end, you're moving the other end. And then finally, there is what she calls united agency. This is sometimes reported by people, for instance, in the context of music performances, but also things like demos, where you really feel like you're one with the group. You're acting as one. And this is something that we still don't understand very well in terms of the mechanisms that are involved. There's interesting sociological work on this, but in terms of the cognitive mechanisms, there's a lot we still need to understand here. I tried to summarize what we know on one slide. Generally, we can say people report more joint agency when they are coordinating with others who are predictable, when the performance is good, when there is synchronization, and cognitive neuroscience research also tells us that when there is stronger interbrain coupling, which we also heard a little bit about yesterday, then people experience more joint agency. It's also important to keep in mind that it's not just the sum of individual agency, it could really be a different experience that we need to study here. And then when it comes to human-robot interaction, there's all kinds of findings, and there seems to be a sort of line of research that suggests there is reduced agency altogether. People feel less in control. But this could have to do with experience, again, with beliefs, with knowledge, and overall the evidence is mixed, so we just need more work in this area. And I want to end by telling you about a project that I'm currently involved in. So we got an ERC proof of concept grant to do something practical for once, and we are developing an app for musicians. So they have virtual partners with whom they're training, and the idea is that to some extent, this might, make it easier for them because they don't need to get together with others to actually practice together, and also it's not piece-specific. They're not practicing particular pieces, but they get trained on general coordination skills. And in particular, what's important in music, especially contemporary music, is the ability to keep self and other apart. So it's not all about coordinating and about feeling joint agency. Often it is also about being apart from others. So for instance, if you have a partner who for some reason is having a difficult time with a piece, you don't want to be overly influenced by them. Or if you have a piece that requires to decouple, like in a lot of Steve Reich music, for instance, that would be the case, you need to really be able to stick to your own part, stick to your own tempo, and not be overly influenced by the other. So we've developed this to help musicians practice this skill. And as we did so, we realized there's one particular virtual partner that people have a lot of difficulties with. And this is a partner who is over-adaptive. So when you go faster, they go faster. When you go slower, they go faster immediately. And at the same time, a partner who's variable. I sometimes call it the bad mother, like someone who's very intrusive and pulling you in all kinds of directions at the same time. And what we realized is that it might actually be generally helpful for people to train with these kinds of partners, not just in a musical context, but perhaps more generally, because if people can learn to regulate when to coordinate, when to be together, and when to be more detached, it might also help them more generally in their social competences and their social interaction skills. But this is work in progress, and we're also out of time. So let me just summarize. The psychological research that we're doing tries to identify particular component processes underlying joint action. We've shown that people have a tendency to include others in their planning. That's also true for robots, as long as they are perceived as intentional. We facilitate coordination by acting in predictable ways, and acting together can generate various interesting experiences of agency that we still need to better understand. And it remains to be further studied what people experience and what they want to experience in human-robot and human-AI interactions, and how we can use technology to train our social skills. Thank you very much, and thank you especially to Christoph for organizing this wonderful event.